In this section, we're going to talk about intensity of sound. Intensity of sound. Intensity is defined to be sound energy per unit perpendicular area per unit time. The definition is energy per unit perpendicular area per unit time. Per unit time. So let's say you've got sound energy falling on this area over here. So the amount of energy that falls on the surface per unit area per unit second is what we call intensity. So mathematically, we're going to use I for intensity. Mathematically, we can say this is the amount of energy per unit perpendicular area per unit time. Okay, now let's write it like this. Area equals, we're going to put the energy over time over here, and then 1 over A perpendicular. Now this one, energy per unit time, is defined to be power. If you remember, power is rate of doing work or rate of transfer of energy, okay? So this is the power of the source, the amount of sound energy produced per unit time by the source. So we're going to substitute for E over T by power, okay? If you remember, the unit of power is watt. Okay, so that we have intensity equals power per unit perpendicular area. Okay, and of course unit of area is meter squared. So it follows that the unit of intensity is watt per meter squared. We're going to use capital W to represent watts, so it'll be watts by meter squared is the unit of intensity. So intensity is defined to be power per unit perpendicular area, or energy per unit area per a unit time. But we're mainly interested on special kind of wave called spherical waves. So let's look at what spherical waves are. Spherical waves are waves that propagate in all directions with the same intensity. These are waves that propagate in all directions with the same intensity. For example, you see, when I speak, I can be heard in all directions. The reason is sound travels in all directions. Okay, so when an object produces sound, the sound will be propagated in all directions. So such a wave, where the wave travels in all directions with the same intensity, is called a spherical wave. Okay, so let's see how we obtain the intensity of a spherical wave. Okay, now you got the source over here and the energy is spreading, okay, like this. So our area is going to be the surface area of a sphere. Okay, so take the radius over here. So if you want to calculate the intensity over here, our area is the surface area of a sphere, which is 4 pi r squared. So for a spherical wave, we have the intensity equals the power of the source divided by 4 pi times radius squared. Okay, so r is the distance between the source and the point at which we're trying to calculate the intensity. All right, so for spherical wave, we can calculate the intensity using this formula. Okay, so as you can see, the intensity varies inversely with the square of the distance. Okay, if the distance doubled, the intensity is reduced by a factor of 4. All right, so it is inversely proportional to the square of the distance. Now let's consider an example. let's say a certain speaker is producing a sound. A certain speaker is producing sound, okay? Now, it's found that the intensity at a distance of 2 meters is, let's say, 40 watts per meter squared. The question is, calculate the intensity at a distance maybe 4 meters. Okay, so now the source is the same. Okay, so that means the power doesn't change. So what we have is intensity for the first situation is power divided by 4 pi r1 squared. Okay, and the intensity for the second situation is I2 equals power divided 4 pi r2 squared. Okay, so what we have is we have r1 2 meters, and the intensity corresponding to that, that's I1, is 40 watt per meter squared. Okay, and then for the second situation we're given the distance, so r2 is 4 meters. The question is calculate the intensity corresponding to 4 meters. Okay, so since power is the same, you know, if you divide this equation by this equation, what do you get? You get I1 over I2 equals 4 pi r2 squared over 4 pi r1 squared. Okay, or the 4 pi cancels out, you get r2 squared divided by r1 squared. Okay, so if you cross multiply, we get I1 r1 squared equals I2 r2 squared. Okay, we're looking for this one, so we have I2 equals I1 times r1 over r2 squared. Okay, so I1 is 40 and r1 is 2, r2 is 4 squared. Okay, so this one is half squared is 1/4, so we get 10 watt per meter squared. So we see that when the distance doubled, the intensity is multiplied by a factor of 1/4. Next, we're going to talk about Doppler's effect. Doppler's effect. First, let me define it. This one has to do with the change in the pitch heard by an observer due to the relative speed between source and observer. Okay, for example, let's say you have a car producing a certain sound over here, and you've got an observer over here. Okay, it's a common experience that if the car is approaching the observer, the pitch of the sound will increase. If the car is going away, the pitch of the sound heard by the observer will decrease. Okay, so what we call Doppler's effect is the change in the pitch heard by the observer due to the relative speed between observer and source. So this is change in the pitch of the sound heard by an observer due to the relative speed between observer and source. So that's the definition of Doppler's effect. If let's say the car is producing sound, if it's approaching the observer, the pitch heard by the observer will increase. If the car is going away, the pitch of the sound that's heard by the observer will decrease. Okay, so we're going to separate this into two cases. Let's start with case 1. Case 1 is going to be observer stationary observer stationary. Let's start with source stationary. Source stationary and observer moving. Observer moving. Okay, so we have the following situation. Let's say this car is producing sound over here, and then we have an observer receiving this sound from the observer. Okay, suppose let's say this car is producing sound at 1000 cycles per second. Okay, so what that means is if this car is producing sound at 1000 per second, the observer will receive sound at 1000 per second. But if the observer runs into the car, if the observer goes this way, then the number of cycles heard by second by the observer will increase. So the frequency heard by the observer will be higher because we'll be receiving more cycles per second. As a result, the pitch of the sound received by the observer, the pitch of the sound heard by the observer increases. Okay? How about if the car moves away? If the car moves away, or rather, if the observer moves away, the number of cycles heard per second will decrease, and then the pitch decreases. Okay, so that's the reason the pitch of the sound heard by the observer decreases. Okay, when the observer approaches the car, he will receive more cycles per second, which results in the increase of the pitch of the sound heard by the observer. If the observer goes away, we will get less number of cycles, and that will decrease the pitch of the sound heard by the observer. Now let's say F represents frequency produced by the source. Frequency produced by the source. Let's say F prime represents frequency heard by the observer. Frequency heard by the observer. Let V represent speed of sound. And let V naught represents speed of the observer. Now, remember, the source, or the car in this case, is stationary. Then we have the following formula for calculating the frequency. F prime equals the frequency produced by the source, and then you've got the speed of sound plus or minus the speed of the observer divided by the speed of sound. Okay, so you've got plus or minus. Okay, you use the plus sign if you expect the pitch to increase. The pitch increases if the observer runs towards the source. Okay, so use the plus signs if the observer approaches the source. Okay, but if the observer goes away from the source, you expect the frequency to decrease, right? So use the minus sign. So use plus sign if observer is approaching the source. Use the minus sign if observer is going away from source. So let's distinguish between the plus and minus. You use plus if observer approaching the source, and use the minus sign if observer is going away from source. Okay, so this is the special case where the observer is stationary, the source is stationary and observer is moving. Okay, let's consider an example. Let's say a stationary car is producing sound of frequency, let's say 1000 cycles per second. Okay, the question is calculate the frequency heard by the observer if the observer is, let's say, going away from the source, let's say with a speed of 10 meters per second, let's say, and let's say temperature is maybe 20 degrees centigrade. Okay, so what you know so far is the frequency produced by the source is 1000 hertz. Okay, and the observer is going away from the source with a speed of 10 meters per second. Okay, that's V observer equals 10 meters per second, and we're looking for the frequency heard by the observer. Okay, now we expect the frequency to decrease, so we're going to use the following formula: F prime equals F, and then we've got V minus V observer divided by V. We're using minus because the observer is going away and we expect the frequency to decrease. Okay, so first we have to calculate the speed of sound, okay, before we can do the calculations. But we have temperature, so we can calculate the speed of sound. So first we can calculate the speed of sound, which is 331 meters per second square root of 1 plus temperature in degrees centigrade divided by 273. Okay, so the speed is going to be 331 meters per second square root of 1 plus 20 over 273. Okay, that's going to be approximately 343 meters per second. Okay, so we have the speed, so now we can calculate the modified frequency. Okay, so you've got F prime equals F V minus V naught divided by V. Okay, that is 343 minus 10 divided by 343 times 1000 times 1000. Okay, maybe I'm probably here 1000 times this difference would be 333 divided by 343. So this would be the frequency heard by the observer. Okay. Now we're going to look at case 2. Case 2, observer stationary and source moving. So in this case what we have is we have this source producing sound moving. We can call the speed of the source, and then you've got observer, which is stationary. Okay, so now obviously if the car is approaching to the observer, the frequency or the pitch of the sound increase. If the car is going away, then the pitch heard by the observer also will decrease. Okay, so what has happened? Well, as the source moves towards the observer, what's going to happen is these two peaks over here, this is the wavelengths over here, they will get closer to each other because the car is moving towards the observer, right? So it's the decrease in the wavelengths or the increase in frequency that produces the change in pitch. Okay, because the car is moving towards the observer, the peaks will get closer and closer to each other. That means the wavelengths will decrease or the frequency will increase. So that will change the pitch of the sound heard by the observer. Or if the car is going away, the peaks of the sound get farther and farther away, and so the wavelengths increase or the frequency decrease. So that's the reason the pitch of the sound heard by the observer would change because of the motion of the source of the sound. Okay, so in this case, Vs is going to represent the speed of source. Speed of source, we have already defined the as a variables. V would be speed of sound, and F would be frequency produced by the source. Okay, we have the following formula. The frequency heard by the observer will be the frequency produced by the source, and then the speed of sound, and the speed of sound plus or minus the speed of the source. Okay, so if observer is stationary and source is moving, this is the formula to use to calculate the modified frequency. Now let's see, when we use the positive, when we use the negative. Okay, when the source approaches the observer, we expect the frequency to increase. Okay, so we have to pick the sign that makes this one smaller. That means we pick the negative. So if the source is approaching source, we have to pick the negative. And if the source is going away, we expect the frequency to decrease, so we have to select the plus sign. Okay, so let's distinguish between the plus and sign. Use the plus if source is moving away. Source is moving away from observer. Okay, and we use the minus sign if source is approaching the observer. Approaching the observer.